So in this video we'll prove that the integers are discrete. And we'll use the following two facts about the integers, among others. We'll use that addition preserves inequalities. So one of our axioms of the integers stated that if n is less than m, then n plus k is less than m plus k. So you can add an integer to both sides of an inequality and preserve that inequality. And we'll also use the theorem we proved previously that 1 is the smallest integer greater than 0. So we'll formulate and prove the discreteness of the integers as follows. Our theorem states that if n and m are integers, then n is strictly less than m plus 1 if and only if n is less than or equal to m. Okay? So notice this is a biconditional. It's an if and only if. And since it's a biconditional, it's actually two theorems stated as one. So we'll have to prove both one direction. If n is strictly less than m plus 1, then n is less than or equal to m. And the other direction, if n is less than or equal to m, then n is strictly less than m plus 1. Okay, so let's prove part 1. We'll prove the direction that if n is strictly less than m plus 1, then n is less than or equal to m. Now, to prove this, we'll reformulate it. We'll prove actually the contrapositive. So another way of saying if n is strictly less than m plus 1, then n is less than or equal to m is to say if n less than or equal to m is not true, then n strictly less than m plus 1 is not true. So we're writing the contrapositive of the statement. Okay? And a more natural way of saying that last statement is that if m is strictly less than n, then m plus 1 is less than or equal to n. And that's the formulation that we're going to prove in this part. So suppose that m is strictly less than n. Alright? Well, that means we can add negative m to both sides. Addition preserves inequalities. So if we add the additive inverse of m to both sides of that equality, we get that 0 is less than n minus m. So if we consider the set of all positive integers, we know that 1 is the minimum element of that set A. Okay? We know that n minus m is in that set A. We know that 1 is the minimum of that set A. So we know that 1 is less than or equal to n minus m. Okay, so that's where we're using that 1 is the smallest integer greater than 0. n minus m we know to be greater than 0. 1 is the smallest integer greater than 0. So we have to have that 1 is less than or equal to n minus m. Right? And then of course we just add m to both sides, and that gives us our result that m plus 1 is less than or equal to n. So that completes the proof of one direction of the theorem. So now we're going to prove that if n is less than or equal to m, then n is strictly less than m plus 1. So assume that n is less than or equal to m. We know that 0 is less than 1. That's something we proved previously. Okay. And so if we add m to both sides of that inequality, that will nearly get us what we want. Okay. That'll give us m is strictly less than m plus 1. And we know that n is less than or equal to m. So putting those two together, we get that n is less than or equal to m is less than m plus 1. Okay, so by transitivity, we know that n is strictly less than m plus 1, as we wanted to prove. And that finishes this video. Thanks for listening.